Hi, this is Nikhilian, Assistant Professor, Department of Civil Engineering, HIT, Mangalore. So, in today's session, I will be continuing the discussion about numericals on losses of prestress. Now, I will consider an example. So, a post-tensioned concrete beam 100 mm wide and 300 mm deep is prestressed by three cables, each cable with 50 mm square and with a stress of 1200 Newton per mm square. All the cables are straight and located 100 mm above from soffit of the beam. If the modular ratio is 6, calculate the loss of prestress in three cables due to elastic shortening of a concrete for the following cases. So first case is simultaneous tensioning and anchoring of all the three cables. Second case, successive tensioning of three cables, that is one at a time. Yes, in this question, the member is a post tensioned concrete beam. So the cross section of a member is 100 mm by 300 mm. So the member is provided with three cables and cross section area of each cable is 50 mm square, and each cable is pre-stressed by stress of 1200 Newton per mm square. So all the three cables are located at a distance of 100 mm above the soffit of the beam. So here he has asked us to calculate the stresses in the cable after losses due to elastic shortening in two cases. One is when all the cables are pulled together, that is when a simultaneous tensioning is done, and second case is successive tensioning is done. Now let us see for the first case, that is when simultaneous tensioning is done. So before that, let us consider this a rectangular beam of 100 mm wide and 300 mm deep. So it is a rectangular beam, therefore y1 is equal to y2. The centroidal axis will lie at a distance of 150 mm from top as well as 150 mm from bottom. So it is given that three cables, 1, 2, 3 cables, and these three cables are located at a distance of 100 mm from the soffit of a beam. So this is bottom of a beam or soffit of a beam. So cables are located at distance of 100 mm from this soffit. From the soffit, the cables are located at a distance of 100 mm. Therefore, the eccentricity of a cables will be 50 mm. So the distance between CG of a member and CG of a cable gives us the eccentricity, that is 50 mm. So firstly, we know the cross section area of a member. It is 100 by 300 mm. Initial stress is given and cross section area of each cable is given, that is cross section area of each cable is 50 mm square, and we need to calculate loss due to elastic shortening. So we know the formula for elastic shortening. So to calculate elastic shortening, first we need to calculate what is stresses developed in the concrete, because the formula for elastic shortening is equal to m into fc. Fc is nothing but compressive stresses in the concrete. So here all the cables are straight cables, therefore eccentricity is only 1. Therefore first let us calculate initial pre-stressing force of a cable. So cross section area of each cable is 50 mm and stress in each cable is 1200 mm. Therefore initial pre-stressing force in each cable is 60 kilonewton. So 60 kilonewtons the initial pre-stressing force which is applied to each cable. So 60 kilonewton for this cable, 60 kilonewton for this cable and 60 kilonewton for this cable. So I is moment of inertia, BD cube by 12. So 100 into 300 cube by 12, which gives 225 into 10 to the power of 6 mm to the power 4. Therefore, compressive stresses in concrete Fc is equal to F naught by A plus F naught E square by I. E is minus 50 because eccentricity is below the centroidal axis and it is minus. So substituting the values of F naught, A, I and E, we will get compressive stresses in the concrete with respect to CGs of a tension steel is equal to 2.66 Newton per mm square. So first let us consider case A, that is all the cables are pulled together. So cables are simultaneously pulled. So when all the cables are pulled together, the loss due to elastic deformation or loss due to elastic shortening will be 0. So in post-tensioned PSC member, under simultaneous tensioning and anchoring of all the three cables, there will be no loss due to elastic deformation. Therefore, loss of prestress due to elastic deformation is equal to 0 for first case. Now coming to the second case. So in the second case, the cables are pulled successively. So cable 1 is first pulled, then cable 2 is pulled and cable 3 is pulled. So in the first case, so in case 2, in first step, this cable is pulled. So this cable is subjected to a force, initial pre-stressing force of 60 kilonewton. So what will happen for the cable, or what will be the loss in the cable when this cable is subjected to 60 kilonewton? So when cable 1 is tensioned and anchored, there is no loss in the stress in cable 1. So when first cable is pulled, there will be no loss in the cable 1 because in post tensioned member, the concrete will be already settled, that is the concrete will be already gained its initial strength, and that means the elastic shortening will already been occurred in the concrete before it is anchored with a cable. Hence, when cable 1 is passed through the ducts and when it is tensioned and anchored, there is no loss due to cable 1. So loss in cable 1 is 0. And now coming to the second cable. So when this cable is pulled with the initial pre-stressing force of 60 kilonewton, then there will be loss in cable 1 and cable 2 will be having 0 loss. So cable 2 is tensioned and anchored, loss of stress in cable 1, no loss of stress in cable 2. So why there will be loss in cable 1 is because when cable 2 is tensioned with 60 kilonewton of pre-stressing force and when it is anchored, compressive stresses are imposed on both the ends of a member. So this compressive stresses which are acting on both the ends of a beam will try to further shorten the concrete member. So there may be some shorten in the length of a concrete member due to the stresses developed on both the faces of a concrete member. So as a result of this, there will be loss in the cable 1 which is already tensioned and cable 2 will be having 0 loss because cable 2 will be anchored after that shortening occurs. Therefore loss in cable 1 is equal to M into Fc. So M is modular ratio, it is given. Fc is compressive stresses in the cable which is 2.667 Newton per mm square. Therefore loss in cable 1 is equal to 16.002 Newton per mm square. Now coming to the third cable. So when third cable is applied with a pre-tensioning force of 60 kilonewton, what will happen? There will be loss in cable 1 and there will be loss in cable 2, but loss in cable 3 will be 0, because when a pre-stressing force of 60 kilonewton is applied for cable 3, again compressive stresses are developed on the faces of a member, and these compressive stresses which are developed on faces of a member on both the ends will try to further shorten the length of a member. So as a result of this, there will be loss of stress in cable 1 and cable 2, which is already tensioned and anchored, and there will be no loss in cable 3 because the cable 3 will be anchored after giving the permission for the shortage of that member, shortage in the length of that member, hence the loss in cable 3 will be 0. Therefore, what will be the loss in cable 1 when cable 3 is tensioned and anchored? That is MFC 16 into 2.67, it is 16.002 Newton per mm square. And what will be the loss in cable 2? It is again same formula, MFC, M is same and FC is same, so 16.02 Newton per mm square. And now what will be the total loss that will be occurring in cable 1? So when cable 1 is pulled, the loss in cable 1 is 0. When cable 2 is pulled, there is a loss in cable 1, that is 16.002. And when cable 3 is pulled, there is a loss in cable 1, and that is 16.002. So total loss occurring in cable 1 is 32.004 Newton per mm square. And loss in cable 2. So when cable 2 is pulled, there is no loss in cable 2, and when cable 3 is pulled, there is a loss in cable 2, that is 16.002 Newton per mm square. So total loss occurring in cable 2 is 16.002 Newton per mm square, and total loss in cable 3 is equal to 0. Therefore, average loss of prestress due to elastic shortening will be equal to 32.004 plus 16.002 divided by 3, where 3 is number of cables. So average loss in each cable is equal to 16.002 Newton per mm square. So this is the average loss that will occur in the cables which is provided in the post tension members. Let us move to the next example. So next example is a post tension rectangular beam 300 mm by 600 mm in cross section is pre-stressed with an initial pre-stress of 950 Newton per mm square. Therefore, 4 cables of each 250 mm square. The cables are situated at 100 mm from the soffit with constant eccentricity. Determine the percentage loss of pre-stress due to concrete. Assume the following. Shrinkage strain of concrete is equal to 2 into 10 to the power of minus 4. M is equal to 6. Ultimate creep strain of concrete is equal to 4 into 10 to the power of minus 6. And the cables are pulled one by one. So in this question, it is given that a post tensioned rectangular beam of cross section 300 by 600 mm is pre-stressed with an initial pre-stress of 950 Newton per mm square. So the beam is having 4 cables and the cross section area of each cable is 250 mm square, and these cables are located at a distance of 100 mm from the soffit. So for this member we need to calculate what is the percentage of loss of pre-stress in the cable. So let us consider a concrete member which is post tensioned rectangular beam of 300 by 600 mm. So it is a rectangular beam, therefore centroidal axis will be at a distance of 300 mm from top as well as from the bottom, that is y1 is equal to y2 is equal to 300 mm. So 4 cables are provided at an distance of 100 mm from the soffit from here. Therefore, the eccentricity of cables with respect to central axis will be 200. From here to here, the distance is 200. That is E is equal to minus 200. So first, let us calculate what are the data required to calculate the different losses. So the data required is we need cross-section area of the member, we need what is the initial pre-stressing force, we need what is moment of inertia, we need what is compressive stresses developed in the concrete with respect to CG of a tension steel. So first let us calculate this data. So firstly, initial pre-stressing force. So in this problem they have given cross-section area of each cable. So cross-section area of one cable is 250 mm square, and each cable is carrying an initial pre-stress of 950 Newton per mm square. Then what is the initial pre-stressing force that is applied for each cable? So the initial pre-stressing force applied for each cable is equal to 250 into 950, that is area into stress. We know stress is equal to load by area or force by area, therefore force is equal to area into stress. Therefore initial pre-stressing force is equal to 237.5 into 10 to the power of 3 Newton or 237.5 kilonewton. So 237.5 kilonewton is the initial pre-stressing force which is applied for each cable. So for this cable a force of 237 kilonewton is applied. For this cable also a force of 237 kilonewton is applied. For this and this cable also the force of 237 kilonewton is applied. Then moment of inertia I is equal to B d cube by 12. So 300 into 600 cube by 12, that will be 5.4 into 10 to the power of 9 mm to the power 4. So E is 200 mm. So loss due to elastic deformation. We know the formula to calculate loss due to elastic deformation, that is M into Fc. So M is given, that is 6, and to calculate Fc we have the formula F naught by A plus F naught E square by I. So F naught is initial pre-stressing force we have calculated in previous step. So substitute the values, we will get what is Fc, that is compressive stresses developed in the concrete with respect to CG of tension steel. So Fc is equal to 3.078 Newton per mm square. So here we will get only one Fc because the cables are straight cables and it is having a constant eccentricity of 200 mm. And now the condition is the cables are pulled one by one. The cables are pulled successively. So first let us consider the first cable. When cable 1 is pulled and anchored, no loss of stress in cable 1. So the losses in cable 1 is 0. Now when cable 2 is pulled and anchored, then there will be loss in cable 1 and loss in cable 2 will be equal to 0. So loss in cable 1 is equal to MFC. So M is 6, FC is 3.078. Substitute the values, we will get 18.468 Newton per mm square. So when cable 2 is pulled, loss in cable 1 will be 18.468 Newton per mm square. And next, what happens when cable 3 is pulled? So when cable 3 is pulled, the loss of stress in cable 3 will be 0 and there is loss of stress in cable 1 and 2. So loss of stress in cable 1 is M into Fc. So M is 6, Fc is 3.078, 18.46 is the loss in cable 1. Similarly, in cable 2, loss is equal to M into Fc. So it will be 18.46 Newton per mm square. Loss in cable 3 will be 0. And coming to the last cable, when last cable is pulled and anchor, there will be loss in cable 1, 2 and 3, and loss in cable 4 will be 0. So what will be the loss in cable 1? So loss in cable 1 will be M into Fc, that is equal to 18.46 Newton per mm square. Loss in cable 2 and loss in cable 3 is same, that is M into Fc, which is equal to 18.46 Newton per mm square. Loss in cable 4 is 0. Therefore, average loss of prestress is equal to 55.404 plus 36.936 plus 18.468 plus 0 divided by 4. So average loss of prestress is equal to 27.702 Newton per mm square. So 55.404 is the loss occurring when cable 4 is pulled, and 36.936 will occur when cable 3 is pulled, and 18.468 is the loss that will occur when cable 2 is pulled, and 0 is the loss that will occur when cable 1 is pulled. So total average loss of a prestress is equal to 27.702 Newton per mm square. Now coming to the second loss, that is loss due to shrinkage. So we know the formula delta S into ES. Delta S is given shrinkage coefficient 2 into 10 to the power of minus 4. Young's modulus of steel is given 2.1 into 10 to the power of 5. Therefore loss due to shrinkage is 42 Newton per mm square. Loss due to creep. So here in the question, creep coefficient is not given. They have given ultimate creep strain. Therefore the formula is delta C into ES. So delta C is C into Fc. So C is ultimate creep strain, that is 4.4 into 10 to the power of minus 6. Fc is stresses in concrete 3.078, and ES is Young's modulus of steel 2.1 into 10 to the power of 5. Therefore loss of prestress due to creep of concrete is equal to 2.46 Newton per mm square. Therefore total loss of prestress occurring in the cable is equal to 27.702. So 27.702 is the average loss of prestress occurring due to elastic shortening. So 42 is the loss due to shrinkage, and 2.46 is the loss due to creep of concrete. Therefore total loss is equal to 70.164 Newton per mm square. Therefore loss of prestress, percentage loss of prestress is equal to total loss divided by initial prestress. So initial prestress is given in the question, it is 950 Newton per mm square, and total loss we have calculated, it is 70.164. Therefore percentage loss of prestress is equal to 7.386%. So this is the percentage loss. So final pre-stressing force. So this final pre-stressing force is equal to 950 minus 70.64 into 250. So 950 is the initial pre-stress minus 70.16. So minus 70.16 is the loss due to minus 70.16 is the loss of prestress due to creep, shrinkage and elastic shortening, and 250 is the cross section area. So final pre-stressing force will be final stress available in the cable into cross section area of a cable. So final stress available in the cable is 950 minus 70 initial pre-stress minus losses of pre-stress. We will get final pre-stress into cross section area of the cable, which gives us final pre-stressing force of 219.9 kilonewton. We shall consider the next example. So the question is, a PSC beam of rectangular section 300 mm by 600 mm is pre-stressed by 5 number of 8 mm dia wires at 50 mm from top and 15 number of 8 dia wires at 85 from soffit. The initial stress in the cable is 1200 Newton per square. Estimate the loss of prestress in the wires due to elastic shortening. Assume M is equal to 6. So here a beam of rectangular section 300 by 600 is provided with two cables. So one cable is provided at top and other cable is provided at bottom. And the top cable consists of 5 number of wires of diameter 8 and bottom cable consists of 15 number of wires of diameter 8 So for this cable we need to estimate the losses of prestress due to elastic shortening. So here the problem is different compared to previous problems. So in previous problems what we were having was the cable was only at top or the cable was only at the bottom, and in this problem we have cables in two positions, one is at top and one is at the bottom. So when cables are provided in such a way, then we should consider CG of a cable. So how to consider CG of a cable we shall see in this problem. So a rectangular beam, width is 300 depth is 600 so central axis lies at a distance of 300 from top and 300 from bottom, that is y1 is equal to y2 is equal to 300 So this is a top cable which is located at a distance of 50 from the top. This is a cable which is located at a distance of 85 from the soffit. So from here to edge of the cable the distance is 85 So in the question they have given initial prestress which is imparted into the cable. So the initial prestress is equal to 1200 Newton per square. Then what is the cross section areas of cable 1 and cable 2? So initial prestress is known, it is given in the question, and if I calculate the cross section area of cable 1 and 2, then I can calculate what is the initial prestressing force that is applied to the cable. So area of steel is equal to 5. So 5 numbers of wires and diameter of each wire is 8. So 5 numbers into 8 diameter, 5 into 8 square by 4 plus 50 number of wires and a diameter of each wire is 8 So area of this bottom cable. Therefore total area of steel is equal to 1005.3 square. So this is square. So 1005.3 square. Therefore cross section area of a beam is equal to 300 into 600, that is 180 into 10 to the power of 3 square. And as I said we need to calculate CG of the cable because we have cables at two different locations. So first let us calculate CG of a cable, and let us calculate CG of a cable with respect to the top fiber. Let us calculate CG of cable with respect to this top fiber. So we know the formula to calculate CG of a cable. It is summation of AY divided by summation of A. Therefore Y bar CGs of these two cables is equal to first cable. Cross section area of first cable is 5 into pi into 8 square by 4, and central distance of the cable with respect to top fiber is 50 So cross section area of top cable and with respect to the top fiber it is the central distance of that cable, plus coming to the bottom cable. So cross section area of this cable is equal to 15 into pi into 8 square by 4, and centroidal distance of this cable with respect to the top fiber is, from here to here it is 50, 250, and from here to here it is 215. So centroidal distance is 515 mm divided by summation of A. So total cross section area of the cable is 1005.3 mm square. Therefore Y bar, centroidal distance or CG of the cable, is equal to 398.75 mm from the top. So CG of these two cables is 398.75 mm from the top. From the top, the CG is lying at 378.57 mm from the top, from here to here. So from here to here, this is the eccentricity of a cable with respect to centroidal axis. So here to here it is eccentricity, it is shown here. Then what is eccentricity? E is equal to y bar minus y1. So from here to here it is y bar, that is CG of a cable from here to, from top fiber here to here. Then I know from here to here it is 300. Therefore y bar minus y1, y bar minus 300, which is equal to y1, I will get what is eccentricity E. So eccentricity E is equal to 98.75 mm. I, moment of inertia, is equal to 300 into 600 cube by 12, that is 5.4 into 10 to the power of 9 mm to the power 4. Fc, compressive stresses in the concrete, is equal to F naught by A plus F naught into E square by I. So the cable is having constant eccentricity because the cables are straight cables. Therefore F naught is equal to 15 into pi into 8 square by 4 into 1200. So Fc is equal to 12.74 Newton per mm square. So 12.74 Newton per mm square is the compressive stresses developed in the concrete with respect to CG of a tension steel. So loss of prestress due to elastic shortening is equal to M into Fc. So M is given, Fc is 12.76, which we have calculated in previous step. Therefore loss due to elastic shortening is equal to 76.44 Newton per mm square. So this is the loss of prestress due to bottom cable. So here we can see we have taken the cross section area of bottom cable because we have calculated, we were calculating the losses of prestress in bottom steel. So bottom steel area and stress in the bottom steel is 1200. We will get pre-stressing force applied F naught in bottom steel. So 76.44 Newton per mm square is the loss of pre-stress in bottom steel. Now considering the top steel, so loss of pre-stress in top steel due to elastic shortening. The formula is M into Fc. So what is Fc for top steel? So Fc is equal to F naught by A plus F naught into E square by I. So here also the cable is having constant eccentricity at the top, that is the cable is straight. Therefore F naught is equal to initial pre-stressing force at top cable is equal to 1200, that is stress in the top cable into cross section area. So stress into area, we will get initial pre-stressing force in the top cable or top steel. Therefore in the next step, Fc is equal to, substituting the value of F naught, A, E and I, we will get Fc is equal to, after this substitution, Fc is equal to 5.15 Newton per mm square. So compressive stresses developed in the concrete with respect to CG of tension steel of top steel is equal to 5.15 Newton per mm square. Therefore, loss due to elastic shortening M into Fc, so 6 into 5.15, which is equal to 30.6 Newton per mm square. So 30.6 Newton per mm square is the loss of prestress in the top steel. So total loss from top and bottom steel is equal to 76.44 plus 30.6, that is 107.04 Newton per mm square is the total loss in the member, considering bottom steel as well as top steel. Therefore, percentage of loss of prestress is equal to 107.04, that is total loss of prestress divided by initial prestress. So initial prestress is E1, it is 1200, and total loss of prestress, it is 107.04 from both the cables into 100. So percentage loss of prestress is equal to 8.92%. So the losses are within permissible limits, hence the member can be satisfactorily used. Now let us see one more example. So the question is, a post tensioned concrete beam 100 mm wide and 300 mm deep has a span of 10 meter. It is successfully trussed and anchored by 3 cables. The cross section of each cable is 200 mm square and initial stress in cable is 1200 Newton per mm square. M is 6. The first cable is parabolic with eccentricity of 50 mm below centroidal axis at the center and 50 mm above the centroidal axis at the support. The second cable is parabolic with 0 eccentricity at support and 50 mm eccentricity at the center. The third cable is straight with uniform eccentricity of 50 mm below centroidal axis. So, below the centroidal axis, estimate the percentage loss of prestress in each of the cable if they are successfully tensioned and anchored. So a post tensioned concrete beam of size 100 mm by 300 mm is provided with 3 cables. So in these 3 cables, each cable is having different eccentricities. So the first cable is a parabolic cable and it is having an eccentricity of 50 mm below the centroidal axis at the midspan and 50 mm above the centroidal axis at the support. So the second cable is a parabolic cable with 0 eccentricity at the support and 50 mm eccentricity at the center. And the third cable is a straight cable with a uniform eccentricity of 50 mm below the centroidal axis. So for this condition, we need to determine what is the percentage loss of prestress in each cable when cables are pulled successively. That is, when we need to calculate percentage of losses in the cables when cable is pulled one after the other. So consider a beam of cross section 100 by 300 mm of span 10 meter. So this is cable 1. It is a parabolic cable. So cable 1, here you can see the numbering as 1. So this cable is having an eccentricity of 50 mm at the midspan, that is below the centroidal axis, and at the support. So this is the centroidal axis, and at the support this cable is having an eccentricity of 50 mm above the centroidal axis. So this is the eccentricity of cable 1 above the centroidal axis up to 50 mm. Now coming to the second cable. So second cable is having 0 eccentricity at the support. So here it is 0 eccentricity at support, and at the midspan it is having an eccentricity of 50 mm below the centroidal axis. So this is cable 2, parabolic cable with 0 eccentricities on either supports and 50 mm eccentricity at the midspan. So this is cable 3, which is having constant eccentricity of 50 mm below the centroidal axis. So we should calculate percentage of losses of prestress when cable 1 is pulled and when cable 2 is pulled and when cable 3 is pulled. So before calculating the percentage losses, first let us calculate the required data like cross-section area of a cable, initial pre-stressing force, compressive stresses in the concrete. So initial pre-stress F naught is equal to 1200 into 200. So 1200 is the initial pre-stress which is given in the question, and 200 is the cross-section area of a cable. So stress into area we will get pre-stressing force, that is 240 kilonewton. Cross-section area is equal to 100 into 300, that is 30 into 10 to the power of 3 mm square. It is the cross-section area of a given beam. Moment of inertia is BD cube by 12, that is 100 into 300 cube by 12, which gives 225 into 10 to the power of 6 mm to the power 4. Now let us consider the loss in first cable due to elastic shortening when it is pulled. So when cable 1 is tensioned and anchored, loss in cable 1 is 0. So cable 1 is tensioned and it is anchored, therefore loss occurring in cable 1 is equal to 0. Now coming to the second cable, when cable 2 is pulled, loss in cable 2 is 0 and loss in cable 1 is having some value. So loss in cable 2 is 0, loss in cable 1 due to elastic shortening is equal to M into Fc. So M is given, it is 6 modular ratio, and Fc is compressive stresses in concrete. So as I said in my previous session and in previous problems, here if I consider cable 1 and cable 2, it is a parabolic cable which is having two different eccentricities at center as well as at the support. So cable 1 is having two eccentricity at center and at the support. Here it is 50 and at the support it is plus 50. Similarly, when I consider cable 2, it is also having two eccentricity. So one eccentricity with respect to the midpoint, that is 50 mm, and with respect to the support the eccentricity is 0. So we are considering two cables, and for two cables we are getting two eccentricities, two different eccentricities. So we shall calculate what is the compressive stresses developed in the concrete due to eccentricity of the support and due to eccentricity of the midspan. So Fc is equal to F naught by A plus F naught into E2 into E1 by I. So E2 E1 means here we have two parabolic cables. So E2 is the eccentricity of cable 2 and E1 is the eccentricity of cable 1. So Fc at the support. So at support we have two eccentricities for from cable 1 and 2. For cable 1 at support the eccentricity is 50, and for cable 2 the eccentricity at support is 0. So F naught we have calculated 240 kilonewton. A cross section area of a member we have calculated. So substitute the values here. E2 is the eccentricity of cable 2 at support. So eccentricity of cable 2 at support is equal to 0. Here you can see the eccentricity of cable 2 at support is 0 and eccentricity of cable 1 at support is 50. So 0 into 50 by I. So 0 multiplied by anything, it is 0. So this term vanishes. Compressive stresses developed in the concrete due to eccentricity at the support is equal to 8 Newton per mm square. Now coming to the midspan. So midspan we have different eccentricity, and what is the compressive stresses developed in the concrete due to eccentricity of the midspan. So Fc at midspan is equal to 240 into 10 to the power of 3 area plus the formula is same, but here E1 and E2 changes. So eccentricity is minus 50 E2, That is, cable 2 is having an eccentricity of minus 50 and cable 1 is having an eccentricity of minus 50. So E2 is minus 50, E1 is minus 50. So I, therefore, compressive stresses developed in the member due to eccentricity of 50 mm at midspan is equal to 10.67 Newton per mm square. So this one is FC2, FC1. So we know the nature of this stress diagram will be parabolic as we have discussed in our previous session. So resultant compressive stresses will be FC2 plus 2 by 3 into FC1 minus FC2. So substitute the values, we will get the resultant compressive stresses 9.78 Newton per mm square. Therefore, loss in cable 1 is equal to M into FC 6 into 9.78. So loss in cable 1 when cable 2 is pulled is 58.68 Newton per mm square. Now coming to the next cable. So when cable 3 is pulled, and anchored, there is no loss in cable 3. So cable 3 will be having zero loss and cable 1 and 2 will suffer from loss due to elastic shortening. Now let us consider cable 2. So what is the loss of prestress in cable 2 due to elastic shortening? So that is M into Fc. So here also when I consider cable 2 and 3, so cable 3 is being pulled and anchored. So due to this there is a loss of cable 2. So now we are considering what is the loss in cable 2 due to the pull of cable 3. So when I consider cable 3 and cable 2, here we have two eccentricities. Eccentricity of cable 2 at midspan is 50 and eccentricity of cable 3 at midspan is 50. Eccentricity of cable 2 at midspan eccentricity of cable 2 at supports is 0 and eccentricity of cable 3 at supports is 50. Therefore E2 and E3 is 50, 50 and here it is 0 and 50. So for cable 2, loss in cable 2, let us consider Fc at the support. So the formula is same, E3 into E2. This changes because we are considering loss in cable 2 due to pulling of cable 3. So Fc is equal to F0 pre-stressing force we have calculated in first step. We have calculated what is cross section area F0 and this I, and E3 eccentricity of cable 3 at the support, it is 50 mm. So cable 3 eccentricity at support is 50 mm, that is minus 50 mm, minus 50, and eccentricity of cable 2 at support is 0. So this term vanishes, therefore Fc at support is equal to 8 Newton per mm square. Now considering the eccentricity at midspan. So Fc at midspan. So substituting the values of F0 A, F0 I and E3 and E2 with respect to midspan. So everything is same. So with respect to midspan, cable 3 is having an eccentricity of 50 and cable 2 is having an eccentricity of 50, that is minus 50, minus 50. And therefore Fc at midspan is equal to 10.67 Newton per mm square. So resultant compressive stresses in concrete is equal to 9.78. So considering this and this, as we have done in previous problem, same equation, we will get resultant force. So resultant compressive stress EFC in concrete is equal to 9.78 Newton per mm square. Therefore loss in cable 2 when cable 3 is pulled and anchored is M is 6 and FC is 9.78. That gives 58.68 Newton per mm square. So when cable 3 is pulled, there will be loss in cable 1 also. So what's the loss in cable 1? So loss in cable 1 due to elastic shortening is equal to M into Fc. So here also we will get two values for FC. One is compressive stresses in the concrete due to eccentricity at the supports, and other one is compressive stresses in the concrete due to eccentricity at the midspan. So FC, the formula is same. Here it is E3 and E1 because we are considering losses in cable 1 when cable 3 is pulled and anchored. So compressive stresses in the concrete when the eccentricities at the support is 50 mm, minus 50 mm and plus 50 mm. So F naught A, substitute the value of F naught A, F naught I, and E3, eccentricity of cable 3 at the support is minus 50. E1, eccentricity of cable 1 at the support is plus 50. It is above the centroidal axis and so it is plus 50 plus 50. Therefore, FC at compressive stresses in the concrete due to eccentricities at the support is equal to 5.33 Newton per mm square. So compressive stresses in the concrete due to eccentricities at the midspan is equal to F naught by A. Substitute the values. So here E3 is E3, that is eccentricity of cable 3 at midspan is minus 50, and E1 eccentricity of cable 1 at midspan is minus 50. So substitute these values. So minus 50 and minus 50, E3 and E1, you will get compressive stresses in the concrete due to eccentricity of midspan is equal to 10.6 Newton per mm square. So resultant FC. So FC2 plus 2 by 3 into FC1 minus FC2. You will get 8.89 Newton per mm square. Therefore, loss due to elastic shortening in the first cable when cable 3 is pulled 6 into 8.89, that is m into FC, which gives 53.34 Newton per mm square. So total loss at each cable. So total loss in cable 1. When cable 1 is pulled, the loss is 0. When cable 2 is pulled, the loss is, see here, when cable 2 is pulled, the loss is 58.68. And when cable 3 is pulled, the loss is 53.34. 53.34. So total loss in cable 1 is 112.02 Newton per mm square. Coming to the second cable. So when cable 2 is pulled, the loss in cable 2 is 0. When cable 3 is pulled, the loss in cable 2 is this one. Loss in cable 2 when cable 3 is pulled and anchored is 58.68 Newton per mm square. So total loss in cable 2 is 58.68 Newton per mm square, and loss in cable 3 is 0. So average loss is equal to total loss 112 plus 58 plus 0 divided by 3, that is number of cables. We will get average loss of prestress in the cables. And he has also asked us to calculate the percentage of loss of prestress in each cable. So let me calculate percentage of loss in cable 1. So what's the total loss in cable 1? Total loss in cable 1 is 112.02, 0, 58.68, 53.34, that is 112.02. This is the total loss in cable 1. What's the total stress applied to the cable? It is 1200. Therefore, total loss in cable 1 divided by initial pre-stress applied to the cable 1200 into 100, which gives 9.3%. So percentage of loss of pre-stress in cable 1 is 9.3%. Similarly, percentage loss in cable 2 is equal to 58. So this is the total loss in cable 2. So total loss of pre-stress in cable 2 divided by initial pre-stress. So initial pre-stress is given in the question, it is 1200. This into 100, that gives 4.9%. So percentage of loss of pre-stress in cable 2 is 4.9%, and percentage loss in cable 3 is 0 because the total loss of pre-stress in cable 3 is 0, and percentage of loss in cable 3 is 0. So here the loss is 9.3 and 4.9 in cable 1 and cable 2, and hence the losses are within permissible limits so that the members can be used satisfactorily in the construction.